Okay, hello everyone. In this video, we continue on the series of elasticity, and this is the third video in the series. And here we'll start with looking at Young modulus, then we'll go over to bulk modulus and shear modulus. So here we see that Young modulus, which is also known as elastic modulus or modulus of elasticity, is a fundamental mechanical property used to quantify stiffness or rigidity of a material. Okay, we use it to know how stiff or how rigid a material is. Okay, it is named after a British scientist, that's Thomas Young, and it represents the material's resistance to elastic deformation when subjected to an applied force. Okay, that's an important point to note. Now, symbolized by E or Y, sometimes we use Y to symbolize it. So kindly note that. It's defined as the ratio of stress, as the symbol to strain. Okay, I already explained what stress is and what strain is in the previous videos. Within the elastic limit or the linear region of stress to strain curve. So that's the formula, E equal to stress over strain. Okay, so we see here Young modulus measures how a material elongates or compresses along its length when subjected to a tensile or compressive stress. I explained that in the other video, respectively. A higher Young modulus indicates a greater stiffness, meaning that the material requires more force to induce deformation. Okay, so this is important for us to note. Now, let's see some key points about Young modulus here. The material property, it is an intrinsic property specific to a material and remains constant for a given material under and remains constant for a given material under specific condition. Okay, so that means Young modulus is constant for each material. Each material has a stiffness. Each material has its stiffness. Now, the elastic behavior, Young modulus is applicable within the linear elastic region of the stress and strain curve, where stress and strain exhibit a proportional relationship according to Hooke's law. Okay, now that's important. So Young modulus is only applicable as long as the elasticity remains in the material. Then the stiffness indicator, materials with Young's modulus value are stiffer and exhibit less deformation under a given load compared to materials with lower values. I think we've mentioned that in the first point. Now the unit of Young modulus is typically measured in pascals or gigapascal. Gigapascal means 10 raised to power 10 raised to power 9 Pascal. Okay, in the SI, that's the Standard International System, or you can measure it in PSI, which means pounds per square inch. Okay, that's the imperial system. But of course, in Nigeria here we use the SI system. Okay, so let's see a calculation here. It says a steel of wire with a cross-sectional area of 0.0008 meters square and a length of 2 meters stretches by 0.02 meter. When a force of 800 newtons is applied, calculate the Young modulus of the steel wire. Now we are given force. We say that Young modulus is stress over strain. E is stress over strain. And we also say that stress is force over area. And strain is extension or change in length all over original length. Okay, so we can still say that it is force times length all over area times extension. Okay, so if we substitute the values, we are going to have the force is 800 newtons So we have 800 multiplied by the length is 2 meters. Now divided by the area is 0.0008. Then multiplied by the extension is stretches by 0.02, so 0.02. Okay, and so calculating that will give us okay, calculating that will give us 10 raised to power 8. So that's 10 raised to the power of 8. Young modulus is Pascal, so Pascal, or you can say 0.1 gigapascal. Okay, so that should lead us to the next question. It says a steel wire with radius of cross section of 0.2 centimeters square and length of 2 meters stretches by 0.02 meters when a force of 500 newtons is applied. Calculate the Young modulus of the wire. Okay, we can continue by saying Young modulus is equal to force times length all over area times extension. So the force applied here is 500, and the length is 0.02 meters. Now divided by area, the area is given in centimeters square, so we can convert that to meters, which is 0.2 times 10 to the power minus 4 to convert centimeter square to meter square. Then multiply by the extension, it stretches by 0.02. Okay, so this is what we have. Okay, that gives us 2.5 times 10 raised to the power 7 Pascal. Okay, so that's the answer to that. Now we see another question here. It says a material experiences a tensile force of 600 newtons, causing a strain of 0.004. So that's the strain. If the material has a cross-sectional area of 0.01 meter squared, calculate the stress and then determine its Young modulus. Also the energy per unit volume. Okay, so we asked for three things. The first we are asked to find is the stress. And we know that stress is equal to force over area. Okay, so our force here is 600 and our area is 0.001 meter squared, sorry. Okay, so that will give us 6 times 10 raised to the power 5 Pascal. That's our stress. Okay, the next question we asked to find is the Young modulus. Young modulus we know is stress over strain. Okay, so the stress we just got to be 6 times 10 to the power 5 Pascal divided by the strain. From the question we see that the strain is 0.004. Okay, if we divide that, that means 6 times 10 to the power 5 divided by 0.004, we are going to get 1.5 times 10 raised to the power 9. Okay, so the answer to this is 1.5 times 10 raised to the power 9 Pascal. Okay, so that is the answer. Now the last question we are asked to find is we have to find the energy per unit volume. Now in the second video we saw that the energy per unit volume is the same thing as half times stress times strain. Okay, so that means the energy per unit volume equal to half times the stress times the strain, okay? Which means half times, our stress is 6 times 10 to the power 5, and the strain is 0.004. Okay, if we calculate that, we get 1200. So the answer is 1200 joules per meter cube, which is the unit for energy per unit volume. Okay, joules per meter cube. Now that is quite interesting. Okay, we see another question here. It says if the cross section of a bar is 2.0 centimeters square and the decrease in temperature is 90 degrees Celsius, find the force if alpha there represents linear expansivity 1.2 times 10 to the power minus 7, and E, which is Young modulus, is 2.0 times 10 to the power 11. Okay, we are asked to find the force. Now let's see. Remember we say that Young modulus is equal to force times length all over area times extension. Okay, but we can see here we are looking for the area, we are given force, but we are given linear expansivity, which is supposed to be change in length all over original length times change in temperature, or you can say extension all over length times change in temperature. So from here we can see that extension over length is equal to alpha theta if you cross multiply. What that means is that length over extension is the same thing as 1 over alpha theta. Okay, so what that means is that my Young modulus now can be written as force all over area times alpha theta. So note this. This can be a formula for Young modulus, force over area times linear expansivity times temperature change, temperature difference. So if we substitute value there, our force is, we are looking for force, so that means making force the subroot of formula, we can say that F is equal to the Young modulus times the area by cross multiplying times the linear expansivity, then times the temperature change. Okay, so let's do a substitution quickly. Okay, so substituting quickly, it means that the force equal to Young modulus is 2.0 times 10 raised to the power 11 multiplied by area. We are given 2 centimeters square. We can convert that, which is 2 times 10 to the power minus 4 meters squared. Then we are given linear expansivity, which is 1.2 times 10 to the power minus 7. Then we multiply the temperature change is 90 degrees Celsius or 90 Kelvin. So if we do that, okay, we get the force here is 432 newtons. Okay, so that's a beautiful one. Okay, so that leads us to bulk modulus. Now, what is bulk modulus? Bulk modulus, K, measures a substance's ability to withstand changes in volume, okay, under an applied pressure. So it is defined as a ratio of the change in pressure to the fractional change in volume. Now that change in pressure is also called the bulk stress. Then the fractional change in volume is what we call bulk strain. Okay, so you can see here that delta P is the bulk stress. The fractional change in volume, which is bulk strain, is change in volume all over original volume. Okay, and which you can now write as this. Now the negative sign is because to change volume is always, the volume always reduces. So that's the reason for the negative sign. Now bulk modulus is typically measured in pascals or gigapascals in the SI system, or in pounds per square inch, that's PSI, in the imperial system, with the same unit with Young modulus. Okay, so there's something we call compressibility. Compressibility refers to a material's susceptibility to a reduction in volume. That means how susceptible a material is to reduction in volume when subjected to an external pressure. So when an external pressure is applied to a material, its susceptibility to compression is what we call compressibility. Okay, it quantifies how easily a substance can be compressed or squeezed when pressure is applied uniformly in all directions. Okay, so you can see compressibility, it is the reciprocal of bulk modulus. So compressibility is equal to 1 over bulk modulus. So please, you note that. Okay, now let's see some calculations here. This one says a material has an initial volume of 5 meter cube and is compressed uniformly by an external pressure of 3 times 10 raised to the power 7 Pascal, resulting in a volume reduction of 0.1 meter cube. Determine the bulk modulus of the material. Now, we've already seen that bulk modulus is equal to volume times change in pressure all over the change in volume. Okay, so the volume from the question is 5 meter cube, that's the initial volume. The change in pressure is 3 times 10 raised to the power 7. Now divided by the change in volume, which is the volume reduction, is 0.1. Okay, if we do that, we're going to have 1.5 times 10 raised to the power 9 Pascal. Okay, so that is what to do in scenarios like this. Now the next question says, a substance with a bulk modulus of 2 gigapascal experiences a volume reduction from 5 centimeter cube to 3 centimeter cube due to applied pressure. Calculate the magnitude of the applied pressure. Okay, this is quite interesting. The bulk modulus is 2 gigapascal, which is the same thing as 2 times 10 raised to the power 9 Pascal. And we are given that the change in volume, the volume reduction is 5 minus 3.5. That means final minus initial. Okay, that gives us 1.5 centimeter cube. Okay, we don't need to change the units since there will be cancellation at the end of the day. So we can say here that bulk modulus is equal to, bulk modulus is equal to pressure times change in volume divided by, sorry, that's not correct. Okay, equal to volume times change in pressure all over volume reduction. So now, since we are looking for the applied pressure, we can say that the applied pressure is equal to bulk modulus by cross multiplication times pressure change divided by the original volume. So in applying that now, we are going to have so that means that my pressure will be equal to, the bulk modulus is 2 gigapascal, which is 2 times 10 raised to the power 9, then multiplied by the volume change is 1.5, then divided by the initial volume is 5 cm cube. Okay, Now volume change is 1.5 cm cube. This is 5 cm cube. You see that the units can cancel out. That is why I didn't bother converting. Now if we multiply both, we are going to get 6 times 10 raised to the power 8 Pascal. Okay, so that's the answer for that question. Now we have another one here. It says if a material has a bulk modulus of 1.5 times 10 raised to the power 10 Pascal and is subjected to a pressure of 6 times 10 raised to the power 6 Pascal, calculate the resulting change in volume. Okay, bulk modulus is volume times pressure change divided by change in volume. Now, if you notice here, we are not given the initial volume, so I can say change in volume over volume, which we call fractional change in volume, is equal to the change in pressure all over bulk modulus. Okay, our change in pressure is 1.5. Okay, no, that is our pressure is 6 times 10 raised to the power 6, then divided by bulk modulus is 1.5 times 10 raised to the power 4, and then that will give us 400. So this is 10 to the power 10, and okay, so that will give us 4 times 10 raised to the power minus 4, which is the answer to the question. So the fractional change in the volume is 4 times 10 raised to the power of negative 4. So let's move on. Now I like us to note that bulk modulus at isothermal process equals to its pressure. This video is not designed to give detailed explanation on how that is, but it's expected for you to know that in an isothermal condition simply means constant temperature. The bulk modulus is equal to the pressure. Okay, and the next point is that bulk modulus at adiabatic condition. Adiabatic process simply means constant heat. A process that takes place in constant heat is equal to gamma times P. Now the gamma there actually means the ratio of specific heat capacity at constant pressure all over specific heat capacity at constant volume. This is just a point to note. Okay, so we move to shear modulus. That should be modulus. Okay, shear modulus, also known as the modulus of rigidity or elastic modulus in shear, is a fundamental mechanical property that describes a material response to shear stress. Okay, it quantifies a substance's resistance to deformation by shear stress when the force is applied parallel to its surface. I showed us in previous videos what that looks like, but that is another indication of what it looks like. So let's move on from here. Now the definition for shear stress is or shear modulus, is defined as the ratio of shear stress to the corresponding shear strain within the material's elastic limit. So based on definition, you can see the diagram there. Okay, so your shear modulus is shear stress over shear strain. Shear stress is force over area. Shear strain is theta. That theta there actually represents extension over length. That means changing length all over. That means changing shear length all over the length. Okay, it's important for us to know that. I'm not saying much here. Okay, so that leads us to the next point, Poisson ratio. What is Poisson ratio? Poisson ratio is the ratio of transverse contraction or expansion, that strain, to longitudinal extension strain in the direction of the stretching force. So you can use the word lateral strain to longitudinal strain. Tensile deformation is considered positive and compressive deformation is considered negative. That means that if the deformation is tensile, it means that the Poisson ratio is positive, but if it is compressive, it is negative. So you can see the formula there. Remember that tensile lateral strain actually is change in diameter all over the diameter. Okay, now divided by longitudinal strain is change in length all over length, which when we divide, we are going to have this. That means length times change in diameter all over diameter times change in length. Okay, we should note this, that Poisson ratio typically ranges between -1 and 0.5 for most materials. Common engineering materials have values between 0 and 0.5, where positive values indicate expansion in the lateral direction when stretched, and negative values represent what? Contraction. That's important to note. Now look at this calculation quickly. It says a material has an axial strain of 0.002 when subjected to an axial stress. If the corresponding lateral strain is minus 0.001, calculate the Poisson ratio. Okay, we already know that Poisson ratio is equal to the lateral strain all over the longitudinal strain. Lateral strain all over the longitudinal strain. Okay, and the lateral strain there is based on the question is negative 0.001. The longitudinal strain is 0.002. So this will give us minus negative 0.5. Okay, so that is the answer to that question. Let's see another question. It says the acrylic plastic rod is 200 millimeter long and 15 millimeters in diameter. If an axial load of 300 newtons is applied to it, determine the change in its length and the change in its diameter. And we are given the material's Young modulus and Poisson ratio are this and this respectively. Okay, now from the Young modulus, we can calculate the change in length. That's because Young modulus is force times change in length all over area times original length. Okay, so let's see. We are given the Young modulus. That means this means that the change in length is equal to the Young modulus times area times original length, now divided by the force. Okay, if we substitute values there, we are going to have the Young modulus is 2.7 gigapascal, which is 2.7 times 10 to the power 9, times the area. The area is, we're not given area, but we can find the area. The area is pi d squared over 4. Okay, pi times the square of the diameter divided by 4. Okay, if we calculate that, we are going to get times the diameter squared, which is 15 meters squared, then divided by 4. Okay, that is 176.73. So this area would give 176.74 millimeter cube, which we can convert. Okay, millimeter square, sorry, and which is the same thing as 176.74 times 10 to the power minus 6. Okay, and that's for the area. Then the length is 200 millimeter. The 200 millimeter there means 0.2 meters. Okay, so everything divided by the force, which is 300. So let's calculate that. So we get the change in length to be 30.132. So we have 30.132. Okay, in meters. That value looks too big.